will talk about parametric equations and parametric differentiation. Primarily with this lesson, you should be able to differentiate parametric equations. Okay, let us first recall something from algebra. That points on the graph of some function is denoted by an ordered pair of numbers x and y, where y can be expressed function of x. Now, oftentimes, the function y equal to f of x is rather complex in form, and that to locate points on the curve of the function, we define x and y as separate functions in terms of a third variable. The third variable is referred to as the parameter. Hence, the ordered pair xy will have x, g function of t, and y, h function of t, where t here acts as the parameter. This pair of equations is called parametric equations. Let us now determine the derivative dy dx given a pair of parametric equations where y is the f function of t and x the g function of t. Then the first derivative of y with respect to x is said to be equal to the ratio of the first derivative of y with respect to t divided by the derivative of x with respect to t. That is, dy dx is the ratio of dy dt to dx dt. Or we have f prime of t divided by g prime of t, provided g prime of t is not equal to 0. Now, if you recall the concept of the differentials, then we can now view dy dx as a ratio of two differentials, the differential of y to the differential of x, and that this particular expression here is now considered as a complex fraction. It is the ratio of the fraction dy divided by dt to the fraction dx divided by dt. So if we are going to determine the second derivative of y with respect to x on the basis of the given pair of parametric equations, then the second derivative of y with respect to x can now be viewed as ratio of the derivative with respect to t of the first derivative of y with respect to x to be divided by dx dt. Or we have this equal to the derivative with respect to t of the first derivative of y with respect to x times dt dx. Okay, for some examples, let us find the derivative of the given parametric equations. And for our first example, we have x given by 8 cosine of t plus 5 cosine of 4t, and y is equal to 8 sine of t minus 5 sine of 4t. So what we need to do first is to differentiate x and y with respect to t. So the derivative of x with respect to t would be given by negative 8 sine of t minus 20 sine of 4t. Recall that the derivative of cosine u is equal to negative sine u times du dx. As to the derivative of y with respect to t, we will have it equal to 8 cosine of t minus 20 sine of 4t. Again, recall that the derivative of sine u is equal to cosine u times du dx. So for the derivative dy dx, we will have it equal to the ratio of dy dt to dx dt. Or we have 8 cosine of t minus 20 cosine of 40 divided by negative 8 sine of t minus 20 sine of 40. Or that would be equal to 4 times the quantity 2 cosine of t minus 5 cosine of 40 divided by negative 4 times the quantity 2 sine of t plus 5 sine of 40. Okay, so that this particular expression here can be simplified to lowest terms, dividing both members of the fraction by the common factor 4, and therefore dy dx is given by the negative of the ratio, the quantity 2 cosine of t minus 5 cosine of 40 divided by the sum 2 sine of t plus 5 sine of 40. For our second example, we are given the pair of parametric equations x is equal to t cubed minus 1 and y is equal to t squared plus t. This time, we will determine the second derivative of y with respect to x. Again, for our solution, we first determine dx dt, differentiating t cubed minus 1 with respect to t to give us 3t squared. And when we differentiate y with respect to t, then the first derivative of y with respect to t would just be equal to 2t plus 1. So that on this basis, the first derivative of y with respect to x would just be the ratio of the first derivative of y with respect to t to the first derivative of x with respect to t. And that would be given by the ratio 2t plus 1 divided by 3t squared. Having determined the first derivative of y with respect to x, we are now ready to obtain the second derivative of y with respect to x. And that is, we differentiate the first derivative of y with respect to x with respect to t. And then multiply this with dt dx. So differentiating 2t plus 1 divided by 3t squared with respect to t, the result would be given by 3t squared times 2 minus 2t plus 1 times 6t divided by the square of 3t squared. This is the derivative with respect to t of the first derivative of y with respect to x. This now is multiplied with dt dx. Now remember, we said last time that dx dt can now be interpreted as a ratio of differentials, so that dt dx will just be the reciprocal of dx dt. And with dx dt equal to 3t squared, then dt dx would equal 1 over 3t squared. So what we need to do now would be to simplify this particular expression here. And when we simplify the expression, then the second derivative of y with respect to x would just be equal to negative 2 times t plus 1 divided by 9 times t to the 5th power. Okay, based on our discussion, we can summarize the following. That the derivative dy dx can now be interpreted as a ratio of differentials dy and dx, or it can be interpreted in terms of ratio of the derivatives. And that given a pair of parametric equations where y is the f function of t and x the g function of t, where t is the parameter, then the derivative dy dx can be taken ratio of dy dt to dx dt, or we can look at it in terms of the product dy dt times dt dx. And that the second derivative of y with respect to x is just the ratio of the derivative with respect to t of the first derivative of y with respect to x divided by dx dt, or we have it in terms of the derivative with respect to t of the first derivative of y with respect to x times dt dx. Okay, that will be all for today. I will see you in the next lesson.